quick. Like I said, we're going for full blocking, and we're talking about the jump instruction today, so it seemed appropriate somehow. Hang on. How's that? Little air drum kit. All right, how's everybody doing? We got the skeleton crew. Right, we got the skeleton crew rolling today because of pushing off from yesterday. So is everybody hearing me on Discord? Oh, I gotta share my screen because I'm a doof. Hang tight.
I can hear you.
All right, thank you. Everyone else is like, screw that guy, let him figure it out himself. I'm not gonna answer. All right, there we go. I'd like to thank Van Halen for this tune. Van Halen owns the copyright, or somebody does anyway. Alrighty. All right, we got to take it back down, and sorry, we got to let go of Van Halen just before Eddie's amazing solo on that tune. Big hit, man. 3 chords. I don't know how they do it. So I think you meant, Zach. Hang on. There we go. You got to spell it right. Might as well jump. That's what we're talking about today. You know, I mean, that rookie mistake on your part. So anyway, hey, for the hardy souls that are here, what do we got? Like half a dozen or more. I mean, you know, it's okay. You're like the studio audience. You know what I mean? You represent the stadium of people who would be here if it was Tuesday instead of Wednesday. But you know, burdens on you, burdens on all of you to be the ones to ask questions or, you know, whatever, mock Zach's comments or something. Okay, so as I recall, we are, let me see. So number one, let me get this going over here.
You can mock me, but don't forget who grades.
That's true. Yeah, keep that in mind when you try to, you know, go harsh on Zach. He is one of the grading forces. Okay, there's the link. And I'm going to go ahead really quick and drop that into the schedule like I like to do so that it's just there for everybody. So I think I mentioned in the did I mention in the announcement that that I was on set yesterday? It was like a quick short trigger request. I don't know if I mentioned it. Anybody want to know what it was like out there yesterday on the set in Goshen, outdoors? Or guess? Anybody? Zach, you want to tell them since we already talked about it?
If you could refer to the general chat, that's a picture relating to Dr. K yesterday.
Let me take a look. That was me. Yes, exactly. Well, you minus the costume, minus the period.
Yes. Imagine a
period.
frozen Pharisee in the Antarctic.
Yeah, exactly.
Wearing sandals, getting frostbite.
Yep. Yeah, it was 19 degrees out, and the answer was that it was cold as hell. Was the short answer. It was 19 degrees, and we're outside in the shade in sandals. With but good news was it wasn't that bad because we couldn't actually like feel anything, you know. So it wasn't painful, you know. Because to feel pain, you have to feel, you know, feel something. Okay, I am actually doing this while I'm yapping. All right, link is now in the schedule. Rock and roll. Okay, all right, we're good. And we're only 2 weeks behind now. No, we're only a week and a half behind. We're only 3 periods. Okay, now let me say one thing. I've had a couple questions about this. We're like, what happens? You know, we're on modules. We're going to jump into module 6 today. We're going to finish module 5, which is chapter 4. We're going to jump into module 6 today in chapter 5. Everything we've done to this point makes everything that follows next kind of much more understandable. But if you look at the schedule, which I know I am, there we go. Let's blow that up. If you take a look at this, we start off just going really slow. It's several weeks, for each chapter, and then even a little bit more, and we just spill out, and that's not uncommon for kind of the way the class goes. But then we start to go like 1 week for chapter 6, 1 week for chapter 7, 1 week, and then module 9 is kind of a day or so where we just talk about design. And then it's 1 week for module 10, 1 week for module 11, and 1 week for module 12. And the reality is module 12 takes like 1 day, like 1 class period. So module 12 is also not as big. It's not, kind of as many points as the earlier modules. And so it does move. Here's, I guess, what I'm trying to say is it moves faster in the sense of, it's module 1 goes this long, and then it's like, here comes module 2 and it's shorter. And then it does it's like a logarithmic scale. But it's not like we covered 1 unit, 1 fixed unit of quantity and took us 3 weeks. And then the next unit of quantity took us 2. And finally we were doing that same unit in half a day or whatever. They're not equivalent. We spend, 2.5 weeks or whatever on module 2 because it's 2.5 times, the size of some other modules in terms of material that we cover. Okay. So they do actually get shorter, smaller, commensurately smaller, and fewer like crazy new ideas, right? When you start off and you're like binary math and the circuits, and there's just so many new concepts you haven't had. By the time you get up to like the stack, it's really, kind of echoes some of the stuff you get in, what's the data structures class? I'm drawing a blank on the number. 20, what is it? 2420? I don't know if that's the number. Anybody? I'm not watching the 2420.
Yeah, it's 2420.
All right, yeah. Okay, so everybody cool with that? The numbers come more rapidly, but the material itself is the same amount. I mean, you're absorbing material at the same pace, but rather than calling this whole thing, 1 that's bigger, and this next thing is 2, and then it's down to like, and 11's like this big. Maybe I need to clean that up, make it more of a linear scale so it's just not confusing to people. You know what I mean? Break that. Because I've kind of got it organized by chapters. But I think, Zach, I think I need to remodularize this thing. I think I do. Okay, Zach, make a note of that and make me do that. And we'd like to thank Jack Nicholson for the cameo in the chat. Just remember, all work and no play makes Jack a dull boy. Which is a Shining reference if you want to know where that picture comes from. Okay, let's do the thing then. All right, everybody cool with that? Any lingering questions on schedule? So we're going to jump into LC-3 right here today. And of course, today is actually we are a week and a half because of fall break. We're 3 class periods behind. It's not entirely unusual. In fact, if we stay all the way up, we usually end with about a week to spare at the end that I just use for like answering random questions and helping students. So it's actually, the pace is not, in the end, not that bad. Okay, let's do it. PowerPoint. All right. So as far as I can remember, we had, let me back up just a little bit. And just sanity check me here, okay? But we had gone through this, as I recall. Right? The kind of the more detailed fetch, decode, execute. And we had gone about how you do the instruction, how you fetch it out of memory. We talked about where that fits in the LC-3 architecture. We talked about decoding. We talked about the instruction cycle, where you have to evaluate the address. And then we talked about this load register, this LDR instruction, and fetching the operands, and then executing the instruction, storing the result if there are any, and then doing it again and again, right? I think we did. My recollection is that we covered all that. Is that anyone want to corroborate if that feels right? And that took us to right here, just changing the sequence of execution. That seems right? Okay. We could go check. We could go look at the last YouTube video. But all right. And so what we're really down to at this point, to wrap up this module, is everything we've done prior to this point has been, what we refer to as sequential execution, right? Because it just goes in sequence, right? You just, you do the, it's like a recipe. Mix the ingredients, do the thing, put it in the oven, set it, whatever, pop it out, check it, And so that's sequential, right? Which is just fine, but, there's just so many things you can't do with purely sequential execution, right? Like, for example, any kind of looping, any kind of do something a bunch of times, right? Now, if you look at this from like a recipe book perspective, right? The recipe might say, I'm going to do whatever, breaded chicken or something, right? And it starts with take your piece of chicken, and it tells you what to do. And it might even sometimes say, do this for all of the pieces of chicken that you have, right? Well, what is that? That's a for loop in nature, right? For all chunks of chicken, do this thing, right? Do the dip thing, put the bread, whatever, place it. For all of the rolls of manicotti, for all of the whatever, and there are recipes or, instructions on how to fix, whatever. You're going to fix your, change your spark plugs. It'll show you how to do one, and then it's for all 6 spark plugs, here's what you do. And that's a for loop, okay? By the way, I got to kill these lights. I leave those on all the time. Hold tight. All right. It's just not as bad on the backlighting, right, to lose that. Right on. So what we have is, previous to this, we've basically identified 2 categories of instruction at the machine level, okay? One of them are operated instructions, which is kind of weird grammar. It sounds funny, operate instruction, like an operating instruction, operational instruction. Anyway, it's called an operate instruction. And that just means that it's just performing an operation. Add this thing, shift the register when you have that. And then there's data movement instruction, which is kind of self-explanatory, right? Load a register out of memory, store a register into memory. Any of those kinds of instructions are data movement. But what we haven't talked about to this point are this category of control instructions, where you actually control the flow of everything, okay, of everything going on. That's what we're talking about. So this is one of those things that is, have any of you just like wondered, like, how do you, I understand now how I add a number, but are you thinking about like, okay, but I can't do much with that, right? Unless I can loop and move around and, get the program flow, right? To kind of do what I want it to do. Even when you were doing like Python, if you were, if I don't know if you thought too much about it, but the actual flow of the program is like set up the for loop, right? For I in range something, right? And then it's like, okay, go boink, 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 do this. And then it's while some condition holds, right? And when that condition is still holding, you go back to the top. The execution flow keeps jumping, the computer's doing this. Well, it is literally doing that, okay? And so the magic secret to all of this, I'm going to go back, actually, you're going to hate me for this, but I'm going back to this picture, okay? Don't hate me for my picture.
It's too late. I already hate you, Dr. K.
Oh,
This picture has nothing to do with it.
Well, I
Go back to your silly picture if you want. You're already irredeemable in my eyes.
I can never hate you, Chris. No matter how you feel about me, I could never hate you. But yeah, so check it out, right? Going back to my dreaded picture, there's this instruction register, right? And the instruction register it's a register, and you can load it from memory. We never push it out to memory. We never store it in memory, although there are some instruction sets that actually will let you, some, machine architectures that will let you store like everything. But in this case, we read it from memory, right? That gives us the instruction. And where do we pull that instruction from? Anybody remember? We have to pull it out of memory, but what tells us where it is in memory?
Would that be the program counter?
Yeah, exactly, right? The program counter just tells us where's the location in physical memory of our next instruction to grab, right? So the program counter, you might recall, is just incremented every time, right? That's that little +1. Do the program counter, increment it. Program counter, increment. Pull it out of there, increment it. So it's just stepping through memory. To do a for loop, all you have to do, like really truly all you have to do, is just put a different value in the program counter. That's it. Like I want this, like I got this routine over there at location, F000, let's just say. There's a routine over there that I want to start running, right? How do I get over there? Well, I just got to put that value into the program counter. If I can do right, because what happens next? Fetch, decode, execute. Turn the crank. Fetch, decode, execute. Fetch, decode, execute. Right? And when it's time to fetch the next instruction, where's it going to go? F000. Go over there, fetch that instruction, and if nothing else happens, it's just going to start incrementing from there. Cool, right? I mean, that's the whole boom factor right there, taking us back. Is that's it? Isn't that? I mean, does that kind of blow anybody's head? I understand that I'm at that stage in my life where I can hide my own Easter eggs, right? And so a lot of things blow my head that maybe shouldn't. Maybe that's a true thing. I'm not sure. But right, I mean, that notion of like, this is the simplest, dumbest, coolest, little tiny idea that I can jump anywhere in the code. But I can also jump conditionally. Like, I only want to jump, like if my value gets below 0. You've seen for loops that do that, right? Start at 10, count down to 1. When you get to 0, I'm done. So, I want to, in some instances, I'm done and I want to just keep going. Other instances, I'm not done. I want to jump back to the top of that loop and do it again until, now I'm done and I drop on through. Okay? That's it. That's the whole secret right there. We just changed the program counter. And the question is, how do I change the program counter? And the answer is, I change it with certain instructions called jump and branch. That's how I do it. So, yeah, this is really what I already said. And we do it with this Van Halen inspired jump instruction. And here's the way this guy works. Okay, now there's jump and branch, and they're just usually in hardware when you're down in the machine level, jump instructions tend to be absolute. Like, look, you get to here, it just says jump, and you go over there. Branch instructions usually are conditional. Like, under a certain condition, go ahead and change the program counter. But if that condition doesn't hold, don't change the program counter. Just let the incremented program counter be the thing. Okay? By the way, one of the things I love about this whole, loading stuff into the program counter is that because of the von Neumann architecture, if I just simply go put a value over there, then the control unit's doing its thing, and it goes, okay, fetch the next instruction, looks in the PC, goes there. It's like a little trick. It's like a behind the back kind of trick. You just simply put a different thing in there. It's like, I don't even know. It's like a hack. It's like a weird hack that tricks the control unit. The control unit doesn't know, doesn't care. It goes wherever you tell it, and it pulls it out, and it starts executing it. Okay, so there's the opcode, 1100, which you can see here in the opcode. It turns out that 11 through 9 are reserved. Okay? And reserved just means, in this case, it means they have to be zeros. It's reserved in the sense that you don't get to touch it, and you shouldn't touch it, and the circuitry, I think, relies upon that being a 0. And then all that's reserved as well, and you don't touch it. The only thing you've got is a base register. You remember we talked about the load R, the LDR, right, which was load a register. So this is a value that has somehow been put into a register, but the value is an address. It's just a 16-bit value, but that's the address, okay? And so in other words, what this instruction does is there's some value sitting in a register, say register 3, right? That value here would be 011, right, if that were register 3. And literally all this operation does is it just goes to register 3, takes that 16-bit value out of register 3, and just puts it in the program counter. That is all it does, period. And the effect is boom factor. And then the control unit goes, okay, ready, let's grab the next instruction, pulls that value out of the program counter, goes over there to memory, pulls it, right? It's a slightly cool concept and a slightly goofy concept, but it's a critical concept to understand software and programming at the most rudimentary level, okay? And that's the jump instruction. And so what I want to end on here, and we're going to come back, by the way, and talk about jumps and branches and build stuff out. But I want to just reiterate that this is the fetch, decode, execute cycle in the context, or written as a state machine for the LC-3's control unit. All right. So if you look at it, this first state says take the program counter, load it into the memory address register out there in memory. Now, again, if we had the big picture, we could reference that, but load that into the MAR. Then we go ahead and we increment the program counter. Right then. We increment it right then. So I think we may have talked about this briefly, but talk to me. Why increment the program counter right then? You don't know what's going to happen, right? There might be a branch instruction later. There might be a jump instruction. Why increment the program counter right now? This is an exam question, by the way. This literally is on the exam. Shall we talk about it for just a second?
Is it because the current instruction is to change the PC? Or
no, we don't know that yet. That's the question, right? Because you don't know if the current instruction, you haven't gotten it because it's on state 3, where we go to the MDR and we pull that value out into the instruction register. We don't even know at this point what it's going to be. Now, let me ask you this. It's a good guess, Stephanie, and everybody else is gutless, right? So, you gotta like throw it out there and then we'll kind of calibrate. But yeah, we really don't know. And we're basically saying, I'm going to increment the program counter every stinking time, whether it's going to be a branch instruction or not. What do you think? And you can go again, Stephanie, if you want. And the rest of the gutless wonders can also. I don't mean that you're not all gutless wonders. Some of you are just courageous but shy, but some of you are gutless, and you know who you are.
I feel called out.
Motivation through shame. I don't know what can we say. No, but what do you think? Right? Why?
So
Are there
as
some instructions that refer specifically and like use the instruction number?
Oh, interesting. So it's an interesting, yeah. That's kind of a yes and no. It's a great guess. And then was that Ison that was just talking? And then Chris, you can go next.
Yeah.
Okay. All right.
Yeah.
And then
That was Chris.
we'll cue it up. Oh wait, that was Chris first, and then Ison's queued up.
yeah,
In any way, I know there were two of you, and I want to make sure that you both
Sure.
get a chance. So, yeah, it turns out that there are instructions that reference the program counter, and they always reference the incremented program counter because the program counter always gets incremented at that point. But that's more just like pragmatic. I mean, like you always increment the program counter, so whenever we have to reference like where I am, I'll always reference it as having already been incremented. But if I didn't increment it right then I would just use the unincremented program counter.
So that's something that we have to adjust for, but it's not the reason for
Exactly, that's right. And we do have to, understand that any time an instruction references the program counter, it always will be the incremented program counter. But that's not why we do it. Exactly. So yeah, next idea.
so with this, I mean, what comes to mind for this, and this is from programming stuff.
Yeah.
I think of recursion as it goes back to its state before, and then it spits it out again. So you fetch something, and then it comes back to that same fetch state. I don't know if that's the right idea, but it's just a thought that I have.
It's a good thought. It's not so number one, understanding recursion at this level is a much more complex thing. You know what I mean?
Okay.
So that's
So
not
I
really
shut up as one of the gutless wonders then. Okay.
no. So you're a courageous wonder.
I'm just kidding.
Yeah, exactly. No, you're a courageous wonder because you threw an idea out, and you're in a sense you're kind of a little bit further ahead, and you got to get into things like stacks and activation records, and you know what I mean, and returns from jumps and crap like that. But no, these are great. These are great ideas because they kind of, they kind of fill in little 3 dimensions around the area. Let me throw it at you this way. I'm going to persist for just another minute or two. What is there? Okay, the first question is, I don't know at the end of the day whether I'm going to just grab the next instruction or whether I'm going to branch or jump, which would cause the next instruction, the PC, to change, right? In essence, I'm going to take the PC, increment it by 1, then it sits there incremented, and if I have a branch instruction that holds true or a jump instruction, I'm going to overwrite it, right? I'm going to overwrite it. So really 2 questions. What are the odds of a branch or jump versus a linear instruction? Let's just start. What would you say? Odds of, what would be the distribution, would you imagine? Any of the gutless wonders are welcome now to jump in.
50-50.
No, I doubt it. Yeah, I don't know a number. I don't know a concrete number. But if I were to guess, I would bet it was 90-10. That maybe only 10% of the instructions are actually branch instructions, or because there's a lot of situations where there's just stuff you got to do, right? Initialize the blah 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 module, blah blah blah. You're just going, and then it's like under some condition. There's right there, and then if it's the one thing, there's like a chunk of code. If it's the other thing, it's a chunk of code. You know what I mean? The actual instructions that are the point of decision, relatively small percentage, right? So number one, it's like, well, the number of times when I overwrite it where I didn't have to, it's actually really, really small. That's sort of one idea. But here's another idea. And great courageous answer, by the way. Just, again, we throw it, you're not supposed to know all this stuff. So just thinking out loud is a way of exploring, right? Here's a more important question. If I do have to overwrite that program counter, I incremented it already, and now I have to overwrite it because it was a branch instruction or a jump instruction. Did I lose anything? Remember that performance, is really, really key. Down in the assembler, there will be optimizations that are just trying to save, 10 microseconds, because you do it a billion times a second or whatever. You're running instructions like crazy, and a few microseconds or a few nanoseconds, nanosecond here and a nanosecond there. Pretty soon you're talking real time, But things do get slow, right? Because they're dumb, and you got to be as kind of greedy and stingy as you can be down at that machine level. That's really a principle when you're doing this kind of low level stuff. So am I making a mistake? Even the 10% of the time, let's say when it is a branch instruction, did we lose anything time-wise by doing that? Again, there's only two answers to that question, which are yes and no.
No, we don't.
See. Why?
God damn it.
Sorry, Chris. I'm pressing, man. I'm pressing. Anybody? You're killing me.
Does it run at the same time by chance? So the +1 incrementing it.
Ding, 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 ding. Yeah, exactly. Here, let me take it back to the picture again. Sorry, Chris. You're gonna have to just watch this happen in real time, right in front of you. But here, look at this. So this is the interesting thing, and it has to do with kind of inherent parallelism built into the system, right? So when I do the normal fetch, decode, execute, right? I load the what do I do? I load the PC. First of all, I got to get it kind of ready. Then I got to trigger this little gate, the control unit does, to allow the program counter to go onto the bus. That's actually one cycle, right? Now, while the PC is being loaded on the bus, what else is happening concurrently in the system right now that we know about? It's also getting incremented over here. So while we're putting it on the bus, it's look, we got downtime. We got to wait for the bus to arrive. I'm going to do another thing. So it's got to go out onto the bus. Then the next step is I got to trigger the MAR to receive it, right? Then I've got to load that MAR over here. Then I got to do all that memory stuff we talked about. Then I got to pull the value out, and that's got to wind up over here in the MDR. You know what I mean? I've got to do, and then I've got to gate that so that the contents of the MDR go onto the bus. Then I got to gate this so that the contents of the bus flow into the instruction register. That's at a real coarse-grained level, that's okay, I got 1 to get it ready, 2 on the bus, 3 I'm in the MAR, 4 I'm touching memory, 5 I'm pulling it into the MDR, 6 I'm putting that value on the bus, 7 that value finally shows up the control in the instruction register. And it's actually more steps than that. But really coarse-grained. It's 7 things. What about, and there's none of that has anything to do with this thing right here, this little increment the PC. How long, so in other words, incrementing the PC could take up to 7 steps and there's nothing lost. There's nothing lost because it's totally concurrent. It happens at exactly the same time. Nothing lost. Then 90% of the time, when you're ready to go, you don't touch the PC and it's already ready to go for the next one. You might as well do it. There's no harm. And then if you have to change it, you change it, no big deal. The other thing I don't know is whether this is architecturally, whether the PC and the value 1 are dropped into the ALU and performed as math, and then whether that's all kind of going out there and coming back inside the control unit in the CPU, or if there's literally just a little incrementer circuit built right here onto the PC. That's possible too, just again for speed. And I don't really know, and I'm sure different architectures would do it differently. But you see how cool that is? And then what actually winds up happening is, see this multiplexer right here? PC mux? If it is a branch instruction, then we get this other, we get values from somewhere else that go into the program counter. In this case, this register file right here, one of these output registers, see it going over here? That's like the load R. I'm going to load the value of a register into the program counter. That would be selecting that option. The other option, kind of default, is there's +1. I'll take that incremented value and load that into the PC. But every time while I'm cycling and while I'm executing the instruction, I have to load a value into the PC from somewhere. This multiplexer makes the control unit, but that multiplexer makes that decision about how to do that, what value gets put into the PC. No blood, no foul. It's free. By the way, if I ask you this question on an exam and you say it's free, props for having been here, but that's not an explanation. You know what I mean? Why should you get a puppy? It's free. That's not a thorough enough explanation. But you know what I mean? You've got to elaborate a little bit. But does that make sense?
Makes sense to me.
All right.
Yeah, seems so. I mean, it's basically we have to wait for this additional information from external sources, so we might as well increment the counter while we're waiting.
That's right. And then you just have to know that that's now your new, remember, everything is a social contract. So all the instructions that are going to start with because it turns out there's a bunch of instructions that reference the current spot that you're running in memory. That way you could have a little routine, and nearby you have local variables, right? Like little, what those are, a little variable defined real close by, right? I can keep that close by so when I'm referencing it, I don't have to go grab a whole register to get that value. I'm just you know what? It's only 5 bytes above the program counter, or it's just 10 bytes below where the program counter is. And I can reference memory that way, that stuff that's close by. So, I just have to make sure that the social contract includes that the program counter has been incremented prior to when the instruction gets executed by the CPU. So it's kind of a dumb little question, but in order to answer it, it just requires that you be just a little deeper about how these things are moving around in this this picture, this little road bus of the campus bus that drives around and carries everything around, and how these little pieces are going. If you look at it, there aren't that many moving parts, really. Okay, and then we ended with that. So here we are. So that's incrementing the PC. We go out. This notation, by the way, when you see it, is that M stands for memory, and that little bracket, the little sub, think of it almost like an array, if that helps, where the index into the array is the memory address register. So it's like the memory at location pointed to by the MAR, grab that and put that into the MDR. Then take the MDR, put that into the instruction register. All of that is the fetch. It starts with the program counter, goes out to memory, gets the contents, puts that into the instruction register. When I have this stuff in the instruction register, then I have done the fetch. Okay? And the instruction register is like a little sushi table. I get all these 16 bits, and I'm like, slicey, slicey, slice. Here we go. I know, I'm looking at the parts. I know what it is. Then we decode it. Now, the decoder, essentially, there's a state machine, and the opcode is the trigger on the decoder. We talked about this already. Literally, the opcode is the lines for a decoder that tell you which thread to follow in the circuit. In this case, we talked about add, we talked about load R, we talked about jump. We talked about one representative of each kind of instruction. If you understand how add worked, how jump worked, and how LDR worked, you kind of are about 70% of the way done with understanding how to program in machine language. Seriously. Anyway, if it's an add, then it's just, the first state for the add. And now you're in the little state machine for the add instruction, down to the last state of that add instruction. Same here for LDR, same over here for jump. And then when you're done with executing that thing, well, and the last thing notice that this jump instruction does after doing all the stuff is it takes whatever the value is in the register and puts it into the program counter. So that the control unit has to do that. And then we're back to state 1, where I go to whatever the PC says. What if I put a random number in the PC? What happens? Rando number.
It'll just grab that from memory, won't it? It won't care
That's
if
right.
it's an instruction. No, for data.
It's just going to go there. It doesn't even care, right? Maybe it's data. It's just going to go there, fetch it, put it in the instruction register. Say, good luck. Right? I mean, it would be just like if somebody said, you know, I got to go to this little self-serve, restaurant kiosk or whatever, right? Or a vending machine. You're like, go to the vending machine, go to location, whatever, you know, put in your 50 cents, pull it out and eat it. And then somebody as a joke just like spins it around and it's, you know, whatever. It's just something, dead leaves or something disgusting, right? And if you're the control unit, if that's where you sent me, I'm just going to open, I'm just going to eat it. You know, it doesn't think about it. It just takes whatever it is and just tries to run it. And once again, social contract, right? Any 16 bits can be viewed as any number of things depending upon how you act. It could be an instruction, could be data, could be a character, could be a couple characters, could be pixel colors, could be anything. So, okay. This screen, which should actually say this screen left intentionally blank, but which does say end of slideshow, is the end of chapter 4, which is the same as module 5. So, Zach, you want to do the magic deadline trigger?
Yeah.
Will you?
Yeah.
Awesome. Just double checking. Because those really are two distinct questions.
Totally won't.
I was trying. No, Zach absolutely will.
So the fourth.
Oh,
How well do you think you can trust Zach?
So far, it's working
Start
out.
getting mouthy, Chris. I know your exams.
I'm gonna have to separate you two. I can see this.
So November 4th, then module 5.
Yeah, man.
Okay.
But
Will
and
do.
the moral of the story again, I don't have to make the fear speech again, do I? No, I'm not gonna do it. I don't have time. But the moral of the story is you gotta keep up. You gotta keep up. You have to keep up. Don't be
The kids who would show up to a lecture on an unexpected day are probably not the kids who aren't doing their homework.
No, that's true. That's right. On the other hand, of course, a lot of YouTubers will still watch and they need this fear speech. But it's the ones who will never listen to this that I am, in fact, the most concerned about. It's like definitional, right? That's kind of a tautology. Okay. Are we ready for the next module? Because this is the module about the LC-3, your little happy computer. And what we're doing now, you understand, actually, we've been through a lot together this semester. You've covered a crap ton of material, a metric crap ton. I really, you know what I mean? Don't you think? Does it feel like that to you? Anybody on overload? There's a lot of concepts coming that are ripping. And now this is another thing. At this point, as we hit machine language, some of you that are really more low-level types are kind of in your heyday. You're in your zenith. You are in your happy place because it's all been about the circuits and the low level and whatever. And then we're going to program in ones and zeros, which is just freak. But it's true. And all computers at the end of the day are programmed in ones and zeros. And then we're going to pivot to assembly language, which is what comes next. And what's really weird is that some of you that have struggled but have made it to this point will get to assembly language and it'll start popping and you're going to be like, okay, thank goodness I can now, like, just as programming, I'm okay. And you're going to be just fine. And some of you that have been like cooking with gas to this point, it's going to get to assembly language and it's going to feel like too high level for you and it's going to freak you out. Believe it or not, there's just some people dig the way low level, some people higher. Some of you will struggle the whole way. Just know that I love you and I have all the sympathy and empathy for you. And then there are some that are never going to struggle with any of it, and we don't know what to say to these people. And there are some who just forgot they were even registered for this class. And that's a different kind of anxiety, but it has nothing to do with the material per se. So here's what we're doing. We're going to take these general... Thank you, Jacob, for the honesty, man. The SR latch, the RS latch. Yeah, it's also an RS latch, Jacob. And this might have been part of the struggle, because if that S and that R are like out of order, right? The gated D latch. Anyway. Yeah, but no, that's right. It can be, it just depends on kind of your mindset. Some things just are easier for different people. That's just the way this thing works, and doesn't make you, smarter or less smart than the next person. But there's kind of an aptitude thing, which is just like what clicks and what doesn't click, and that's just a real thing. That is just part of life. Everybody has different things that they dig that click for them. So here's what we're going to do with the instruction set architecture. This gets abbreviated ISA sometimes. I'm never going to pin you to these acronyms, these TLAs. But the instruction set architecture involves sort of broadly speaking 3 things. And this becomes really relevant to, to understanding the LC-3 or any processor for that matter, which is one is how's the memory set up? Right? Remember all the things we talked about? Addressability, how many bits are in each memory address, the address space, right? There's just these ideas about how you do that relative to the memory. The other one is register set. Are they general purpose? Are they special purpose? Are there 8 of them like the LC-3, or are there more? There's never less, really. I don't think. And then what's the instruction set look like, right? What are the actual instructions, the opcodes, the addressing modes, the data types, that kind of stuff. So what we're doing in this lecture is we're breaking down the LC-3 specifically, okay? So in this one, we're just saying, okay, let's talk about, we've talked in general about memory, and these kinds of things. Let's talk specifically about the LC-3 and what its features look like so that you can, start understanding how to program. And I just remembered somebody, I can't remember, Zach, if it was you and me talking about it or if it was a student that pinged me. I cannot remember, but it had to do with understanding things like when the homework this is back a couple modules, but when the homework talks about, memory as a function of n, like what's, how many numbers can you represent with n values? Was that one of you students that pinged me about that, or... I don't remember. If it's not a real thing to anybody who's on right now, I'll defer it. And the other thing I should say is that we can always do a help section on a subject. If there are folks that are like, I'm still on module 2 or 3, but by golly, I'm going and I'm going to make it, and I'm going to, but I just need a little extra help. We can also just do some rando help sections, that we can set up at odd times in the evening or whatever on certain topics. So we can certainly do that. Okay. Just got to ping me so we can schedule it. Okay. This is what we're going to talk about right now. So here we go. LC-3. These details will become really obvious and kind of second nature once you start programming with the LC-3. Oh, and let me do this real quick. I want to really quick. If you search for right there, I don't know if you can see it. Let me kind of blow it up. If you just go onto your favorite search engine and you just go LC-3 simulator, it's always the first hit, and it is a GitHub repository. Okay, well, if you go here, the way this pops up, it just runs. Boom. And major kudos to the guy. If you want to go to the actual GitHub repository and look at the code, look at whatever, you can do that. So I want to just point you, as soon as we start programming in the LC-3, then this thing becomes kind of your best friend. Okay? You don't have to do, you can do a lot of that programming on paper, try to work it out, and see what it does and kind of manually go through, and I call it playing, Oh, is that a pin? Thank you, Tyler. So that LC-3 page is a pinned message for the server. Awesome. I had forgotten that. But fortunately, it's not the only thing I've forgotten. So it's in really good company. But let's take a look here. And what I really like about, first of all, it's a fine simulator / emulator. It's really nice. And kudos to can't remember the guy's name who did it. It's over there again. It's in the GitHub repository. There are actually a couple changes I want to make to it to make a couple of programming things just a little bit easier that don't contradict or conflict with the architecture of the machine. But what I want you to do, and this is just kind of unofficial assignment, is just go play with this. What you'll see is these memory addresses, right here. One thing I don't like is this interface for scrolling is clunk. Okay, it's scrolling you up in memory, up and down in memory and I don't like the interface on that at all. But what you can see is you can put actual values in here. Like I can just click on that and just drop a value. That's hex, but hex is just binary in a different view, right? Hex is just another way to view binary.
Condensed binary.
Right, yeah. It's a notation, right? Every 4 bits I throw a digit and it's just easier to read. So here's all the registers. There's the program counter. Notice program counter is just sitting right there at 3000. There's the instruction register with nothing in it. We haven't talked about control codes. We haven't talked about PSR. But there's registers 0 through 7 with nothing in them. And then I can just, I can also do this thing where I can put assembly language right here and paste it in. Or I can go raw and it's like paste your hex or binary code below. So when you're writing code in binary, use this. It's fair. It's not cheating. Put what you think is the binary code, drop it in and run it, and see it actually run. If you'll spend some time in that, like every day, or every 2 days, just it's got to be fluency acquisition. You'll find that it just really becomes second nature. But it doesn't without spending the time. That's kind of the law of the harvest, and it doesn't work if you don't spend the time. So just start by search for LC-3 simulator. I don't even have it bookmarked. I just search for LC-3 simulator every time. And that's kind of a recommendation, okay, to you to get you good at the LC-3. And starting like now, this becomes important, pretty important. Okay, so back to the LC-3. And we'll do a little bit of live. I want to be able to jump to that every so often. When we're talking about ideas, how does that one thing work? What's really going on? We'll write some code, drop it in there, step through it, and you'll see exactly what's going on. Okay, memory. Let me see. Now, because I am a thrill seeker, hang on a second. I want so desperately to get blocked on YouTube that I'm dropping this in. What's that?
I know it's on Green Play.
Yeah, no, it's right here. Yeah, man. This is
It's funny when we were talking about memory, this very song came to my mind.
yeah. I love this. I love this song. Now, for extra bonus points, when we got a little time, I'll pull up my guitar and play along. It's great. It's also got a really cool bass line, which I can also play, which is really fun. And once every 3 to 4 months, when my throat and my mood are just right, I can actually hit that vocal. And then the rest of the time, it's really not a good thing to try. But I know people who can. Okay, so here we go. Address space. 2 to the 16th locations. Why? Because there's a 16-bit address. Now, here's the confusing thing. The good news is pretty much everything we're ever going to talk about in the LC-3 is 16 bits. That's the good news. The bad news becomes really, really difficult to separate, what's the what. Yeah, jam session time, Zach. It's really hard to separate when everything's 16 bits. Like, wait, what's the one thing? What's this mean? What's that mean? Okay. The address space of 2 to the 16 locations. I don't even know. I think I maybe have a slide coming up here. But what does that suggest for the size of the MAR? What say you? I got 2 to the 16th locations. How big does the MAR have to be?
16 bits.
Boom. That's it. 16 bits, right? If I have 16 bits, if I have n bits in an address, then I can add address 2 to the n locations. Because given n bits, right, I always have 2 to the n combinations. And when I'm dealing with memory, I really think of it always as unsigned, right? The first memory location is 0, right? And the last one is 1111. These are not 2's complement numbers. The notation is really unsigned, if you want to look at it that way. Or you can even just think of it as like the notation is memory. You know what I mean? Which is really just an unsigned value. Starts at 0, it goes to all ones, and that's it. So now, addressability. So that gives me about 64K locations, or this exact number, 65,536 locations. Addressability means how many bits are at every word in memory. Okay? That addressability is 16 bits, meaning that there are 2 bytes in every location in memory. There are 2 bytes. Okay? If we go back to that LC-3, you notice that every one of those locations showed 4 hex digits, right? It would go X and then 4 values. Now, we talked about X just means that's a hex value. It's just notation for us. And then comes 4 hex digits, right? Well, every hex digit represents 4 bits. So every 2 hex digits is a byte. So 1 byte, 2 bytes. So there's 2 bytes in every location in memory. So how many bytes of memory are in the LC-3 computer? Given this information, how many bytes are in the computer? How much RAM is there?
Would that be like the 65K times 16?
Ish, very close. the question is how many bytes. So it wouldn't be times 16 because there aren't 16 bytes at every location, right? So we do know that we've got 65,000 boxes, 65,000 mailboxes, 65,000 slots, right? AKA 64K, because these are, powers of 2, right? 64K locations. At every location, there are 2 bytes. So how many total bytes of memory are there? Bueller?
Would it just be half of that?
Ooh, so close.
32,000, something like that?
No, that's if there was only half a byte at every location.
Oh.
Isn't it 16 kilobytes?
No,
128?
128. If we break it down, what's that? 128K. So the 128K of RAM. Put another way, look, if I got 10 boxes and I tell you that there's 2 chickens in every box, how many chickens do I have? 10 boxes, 2 chickens in every box. How many chickens do I have?
6.
I am gonna. Who said? I'm gonna punch you.
400.
I'm gonna punch you in the chicken. Yeah. Right.
20 seconds.
Anyway, unfair question. Yeah.
Got 20.
Yeah.
20
right.
chickens.
Yeah. 20. Exactly. I know I was like slow pitching an egg, not a boiled egg, but a raw one. Slow pitching the eggs. No, right. That's it. I got this many spots. There's 2 bytes at every spot, so it's twice as many of those things as there are, total as there are spots. That's it. So there's 128K. But it really is that same principle going all the way back to module 2 about, how many combinations are there? There's 2 to the n, right? If n is the number of bits, there's 2 to the n combinations. It's that kind of stuff. Okay. Chickens. Okay. Here's the registers. We talked about this, right? Going out to memory, right? All that crap, get it on the bus, pull it off the bus, MAR, into the memory, MDR, back on the bus, right? That's a lot of steps. Registers, they're just right there cozy, right up, it's like right there in my pocket. Boom, register. Single clock cycle. So we've got 8 this GPR, general purpose register. I will not usually say GPR or general purpose register. I'll just usually say registers, which is a little ambiguous. I mean, there's an instruction register and a program counter, which is a register. And there's control codes, which are actually 3 1-bit registers. So there's this notion of registers as being memory. But when we refer to the registers, we're talking about the general purpose registers. Okay. Every register is 16 bits. Now, here's why that makes sense and is super convenient. If you think about this for a second, we already know that the address size is 16 bits, right? So we already know that the program counter needs to be 16 bits. We know that, right? And we also know that there's 16 bits at every location in memory. So the MDR needs to be 16 bits. Also, the instruction register needs to be 16 bits. So, I mean, it just happens, it's like everybody's 16, but they're not the same 16, if that makes sense. In other words, the 16 bits in every memory location, that sort of suggests that the MDR has to be 16, the instruction register has to be 16, and a general purpose register to receive that data has to be 16. Then there's the address scheme of 16 bits for addresses. That suggests that the program counter has to be 16, the MAR has to be 16, and it would be super convenient if the registers were also 16, so I could do math calculation and shove that into the program counter. So it's really convenient that those are all the same. And you need to understand, too, that they're just not always the same in all architectures, okay? But it is true that the MAR has to have, the MAR and the PC have to be the same. You see that? And the instruction register and the MDR have to be the same because they both hold data. And the PC and the MAR both hold addresses. For the registers, it kind of depends. Super convenient for us that they're all just 16. Okay? Oh, yeah, your favorite picture. Why do I have this here? I don't even know.
I'm gonna cry.
It's probably because of what I was just saying. I think this is my graphic for what I just did without it.
Wait, that looks very familiar.
I know. It's a radical new thing I'd like to introduce you
Am I
to.
having deja vu?
Yes, you are. There's that program counter. There's that MAR. They're both addresses. There is that MDR. There is that instruction register. They're both data. These guys are all 16, which is super convenient because I can fiddle with the PC in here, put stuff into the PC, and I can grab data, put it in there, take stuff out of there and put it back out into memory. So it's really convenient that it's all 16. There we go. Good enough. End of deja vu. All right. Now, here's what we're going to do. And how are we doing on time? We got about 10. I'm going to go just a little over. I was going to go over all the time. Oh my gosh. I took that call, right? At the end of class last time?
You did.
It was important. It was a medical thing, and you know how those guys are, right? You can,
Oh, yeah.
you can never get through. And you call, and they're like, yeah, the doctor will call you, right? You know, like, oh, the doctor's going to call me. Well, this is going to be on his schedule, not mine. You know, or I can not take the call and wait another week or something. And we were close. It was at the end. And by the way, my call did actually go on YouTube. So a couple probably enjoyed that. I did edit that out at the end of YouTube. I don't really care if people want to hear about my, injections in my back. And I don't really care. But it's edited anyway for now. But I muted Discord and I didn't stop the YouTube recording quick enough. Anyway, it's all good. But yeah, apologies. So that was a day when we didn't go late when I was intending to, just to try to do a little more catch up. But we'll do a little. I can go about 10 minutes late today, 5:10. I got a call at 2:30. Kind of got a hard stop. Here's the add instruction. Okay, now if you happen to have handy the cheat sheet that I threw up last time, the little, can you see my impersonation of a cheat sheet? It's that one with the opcodes from the LC-3, and I'll pull mine up as well.
Yeah, it's in the very back of the book, right?
That's right. It's in the back of the book, and I put a PDF of it up on Canvas. And there it is. Okay. Trying to make that. In fact, let me get rid of that. Yeah, there's the instructions. We'll kind of just have this close by so we can, reference it if we need to. But so we're going to do an add instruction, okay? Where are we at? It's going to go away as soon as I do that, but it's all right. All right, there's our opcode. And you might note that is the opcode for the add instruction right there. Okay? It's an add instruction. Why? Like, why are they, remember again, like, how does the computer know what these values are? Well, because this was in memory at the location pointed to by the program counter. Pulled it out. The first 4 bits were 0001, and it said, hey, add instruction. It's really just no more complex than that. But it wasn't. It was actually just the value of a pixel. Well, not anymore. Might have been a pixel going in, but it's an instruction right now, right? Well, it was an ASCII value. But not anymore. Not since the program counter pointed to it, It's all just context, and it all comes back to the control unit. Okay, so where am I? All right. What happens next? There we go. We're going to just kind of show an example, right? So bit 5 is 0. Let's take a look at that. Bit 5, if you remember, could either be a 0 or a 1 in the add instruction. And if it's a 0, it means we've got these two reserved, and then there's a source register too. Otherwise, it's an immediate value, which means it's the 5 bits right there, 2's complement number. That's the number right there. Okay? So this guy is going to be source 2. And so as soon as we put the 0 there, we know that these guys are reserved, that that's the destination register, those 3 bits, that this is the source register 1, and that this is source register 2. These are the 2 operands, 1 and 2. Cool enough? And I just loaded this up with some rando data that doesn't mean anything at all. Okay? As far as we know, it probably means something to the program running it. Next up, I'm going to say in my instruction that this is going to be 0, 1, 0. That is register dos. Boom. So that's going to be the register 2. That's where we're going to put our answer. SR1 is all zeros, which means it's referring to register 0. SR2 is 001, which means it's referring to register 1. So again, social contract, all this says, it's a language. And the language says, okay, control unit, here's what, when I say to the computer, 0001010000000001, in the words of Strongbad, I'm talking technology, but I actually am, because will I literally just say those 16 numbers, 0 and 1, to the computer, what I'm actually saying is, okay, computer, here's what I'd like you to do. I'd like you to take the contents in register 0. I'd like you to add it to the contents of register 1. I'd like you to add those together, put the result into register 2. Done. That's what I want you to do. It's just a language. It's just that 00111101, that means these things to the computer. Cool, right? So I take the contents of our 0, which is that. Conveniently, it's a 1. That was no accident, I assure you. I know because I made the slides. I wanted the math to come out without a lot of complication. Here's our 1 right there. Also, very convenient. Want to add them together. And I want to put the results right over there. That's it. That's what that instruction does. Everybody cool? And if that's anyway, it's good stuff. Okay.
So it's as simple as taking register 0 and then adding it to register 1, and then you get register 2.
Let's say it more accurately. You take the contents of register 1, just so there's no confusion about what you mean when you say take register 1. You know what I mean? Because register 1 is also this 3-bit value that represents a number between 0 and 7 that is the representative of which register we're talking about. See what I mean? There's like that register 1. There's also the contents at register 1. A little bit like saying, so you take
You can't say register because you have to say the content of it, right?
To be more accurate, I mean, to be unambiguous.
Well, if you just said register 1, then the computer doesn't know what that means unless you tell it the contents of it. I get that.
Yeah,
sure.
Exactly. And when I say 001, I do tell the computer I mean register 1. The add instruction knows I also knows I mean the contents of it. So the context of what we mean when we say register 1 changes. So it's more about just that being a little pedantic and precise in saying it. So also from a learning perspective, so that the concepts are not like fuzzed. Because a lot of times when you get really screwed up and kind of wrapped around your axle, when you're trying to do this kind of programming and stuff, it's because it's really not crystal clear in your head. And then whenever it happens to not be quite right, you'll be chasing your tail with the programming and it won't work. And you won't know why. And it's because it actually, as Inigo Montoya said famously, I don't think that word means what you think it means. And that's the confusion. But so to clarify that and to kind of reiterate what you just said, it says take the contents of register 1, add that to the contents of register 0, and take that sum. This is my impersonation of a sum, and then put that into register 2. And overwrite the contents of register 2. Register 2's previous contents, gone. Just gone, never to be seen or heard from again.
Sweet.
The bits themselves are actually taken down by the computer and burned as kindling in a small fire. That's where the bits get disposed of. They're just gone. So, all right, that's an ad. Everybody cool with that? I know this is not like crazy rocket science, right? But is there just anything that's like a clarifying question or any lingering confusion for anybody? You don't have to have lingering confusion. But if you do, please jump in. Okay. Now, I got 4 bits, right? I got 4 bits for my opcode. That means I could max out at 16 different instructions. Max possible. The LC-3 actually has 15. Let's take a look. If you line these up numerically, you could actually count your way through, right? Like that would be 1, there's 2, there's 3, there's 4. See what I mean? I mean, they're all represented. They're just alphabetical by instruction name. And there's traps. So, I mean, if we wanted to count them up, it'd be 1, 2, 3, 4, 5. These are the same opcode. That's 5. 6. No, actually, no. There's 15 instructions, including a couple that share the same opcode. Is that right? No. I'm making crap up. Hang on a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the same. 13, 14, 15, 16. Yeah, no, it's 16. And that includes this reserved. Did I count right? I feel like I'm suddenly on a hallucinogenic trip of some sort. Wait, just the opcodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. No, they overlap. They share. Oh, somebody want to help me? No, it's this JSR and JSR. It doesn't matter. Bottom line, there are 15 opcodes that 15 instructions that actually get used as opcodes, and there's that last one is reserved. We don't use it, so we don't use all 16. The math works, but I just feel like I don't want to do this anymore. I don't want to count anymore in public. You can do it though, and then like sanity check me later. Either via audio or, in the chat. Okay, now the operands. So I've got 4 bits for the opcodes. There's 12 bits for the operands, meaning everything else is what that's referring to. All right. Now, one of the things we want to talk about is addressing mode, which is where do I get the operands? Okay. Where are we at? Okay. First of all, understand that the opcodes in the LC-3, it's a very, very small set of opcodes. 15, 16, that's tiny, tiny, tiny. Most what do you call them? Just instruction set architectures have a much bigger sort of a thing. For example, if I can find... Where is it? Yeah, I've thrown this at you before, but this is the ARM version 8M architecture reference manual. This is the processor that's used in the Raspberry Pi. Okay, this is not on the exam, but I'm just trying to show this to you, and I think I've pulled this up at least once to like scare you with it. But if you look at here, the programmer's model, that, there's the registers. Let's look at that real quick. General purpose registers. Oh, check it out. There's 12 of them. 13, actually. R0 to R12. There's a stack pointer, a link register. There's the program. Oh, check it out. I don't think I actually knew this. In the Raspberry Pi, the program counter is just a general purpose register. So you can manipulate the heck out of that thing. That's cool. There are a bunch of memory map registers, which we haven't talked about. Every register is 32 bits. So it's 4 bytes in every register instead of 2. And a whole bunch of stuff about that. Okay. Then the other thing I was just going to look at was the instructions. What's the opcode look like? There's floating point support. There's the memory model, right? The address space, all that kind of stuff. If we take a peek, address space. Okay, it's a single flat address space of 2 to the 32 bytes. Okay? Which means how big does the address have to be in an ARM? Bueller? What say you? Rock your courage. Find your courage. Come on. Are you talking and I can't hear you? Discord does that to me sometimes.
What was the question?
Okay, I could hear that. The question is, we're in the Raspberry Pi, the ARM processor. It says that the address space is a single flat address space of 2 to the 32 bytes. Okay? And when they say it's just a flat address space, and I think that's saying that it's byte addressable, which means every word is actually just 1 byte. Nah, that can't be. Anyway, but there's an address space of 2 to the 32 bytes. How many addresses would you need? Sorry, how many bits would you need to represent that address space?
Is it
34?
Nope.
Would it be double that? So
No. Yeah, when
Or-
they say byte addresses or it's flat, it's I think they're saying that it's byte addressable, so that every address refers to a single byte. So then there are 2 to the 32 addresses. Okay? So how many bits does your address have to be?
32?
Ding ding ding. 32. Yep. 32 bits in an address. Now, going back, remember when we showed you the program counter, which was register 15, and all the registers were 32 bits. They said all the registers were 32 bits. So that address fits in there. Anyway, just little bits of, you see how these principles that we're talking about, the mythical LC-3 computer that doesn't really exist, but you go to a real processor like the ARM that's used in the Raspberry Pi, what do you see? Address space, addressability, stuff like 2 to the 32. The byte addresses can be they're unsigned numbers in the range of from 0 to up to 2 to the 32 minus 1. Does that look like something that Dr. K threw at you in the homework and in the exams early? You know what I mean? I mean, it's the same stuff. And all I wanted to check, we're really low on time, but I just wanted to check how big the opcode was in the instruction. That's the memory model. System address. Instruction set. Here we go. Let's go here. And the title. I don't need a legend. Come on. Come on. Yeah, and you're like, okay, Dr. K, why don't you just search for opcode? And the answer is because I wanted to just have this experience of looking at this video for a sec. And then I'll just give up and it'll be assembly language, blah, 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 opcode. Okay. The opcode. Let me see, that's a coprocessor opcode in the range of 0 to 15. Okay. So how many bits in the opcode? Or how many bits are used in the LC-3? We use 4 bits for the opcode. In the ARM processor, how many bits for the opcode? I know it's a slow pitch for some of you, but just say it because we got to move on.
4.
We have 4 in the LC-3. How many are there in the ARM processor? Here's a hint. They're numbered from 0 to 15.
Seems like it'd be 4 as well.
No.
Are you saying it goes from 0 to 15, like the
Yeah.
addresses?
No, yeah, I'm saying the bits themselves are numbered from 0 to 15. Anyway,
So would there be
Oh,
there are 16
okay.
bits. There are
So
16 bits in the opcode. So our LC-3 is 4. The ARM processor is 16, 4 times as many opcodes. So how many total possible opcodes could you have? We're going to end on this.
2 to the 16th?
2 to the 16th, which is going to be quick. You can do this one in your head. 2 to the 10th is what? Real quick.
1024?
1K. 1024, but also you can just say 1K. 2 to the 6th is what?
64,000.
That's 64,000.
65,536, just like was discussed before.
Yep, exactly. 64K possible instructions. That's a lot. All right, my friends, that's it. We are out. I got a call to jump on, and hopefully that's been super fantastic. And that's it for today, man. Do we need some music to take us out? What do we want? Okay, I'm going to do this one, and the only reason is because I'm not going to tell you who I voted for president, but I'm going to give you a hint. You know I did. You know I did this. For real.
You voted for Kanye West?
That's where I'm at politically at this stage in my life. I have lost all possible hope in everything involving our political system. That's where I'm at. Besides, this is just such a great song anyway. Yeah, man, Kanye's my man. I think he's going to make a great president. As good as any of the other options at this stage.
Take him any day over the other two.
What's that?
I take him any day over the other two.
That's where I'm at. That was really what it came to. I was doing my ballot, literally.
The Alzheimer guy who sniffs people, or the really grumpy orange guy?
Or the really creepy guy who like sexually assaults people. I mean, pick your poison, man. It's all creepy. Yeah, Kanye. He's also just absolutely batshit crazy, you know. And I don't even care. I don't even care.
Wait, I got something for you, man.
Okay, are you gonna throw it down? I can fade Kanye while I get ready for my call.
Yeah.
All right, and I'm gonna jump off of. Yeah, I just made a public confession on YouTube, but really, that's where I'm at. So, sue me, right?